Morning, everybody. Morning. How was your weekend? Passing?
I silenced the words in the middle.
There you go. I had a terrible weekend, actually. My best friend's son is making life choices, is making it difficult on them, and in turn, my family as well. So we were dealing with that all weekend. Really?
Must have been fun.
Yeah. So, what's that? 18. Kind of explains everything. So yeah, we're worried about our friends, all that sort of stuff. But this is life, right? And so you look forward. When you got a weekend where you look forward to quantum mechanics. It's been that kind of weekend. So I don't want to say that. That's right. So what we're going to do today is we are going to take what seems like a break from the quantum mechanics we've been doing, and we are going to talk, we're going to get more into the history, okay, because there's actually quite a bit of history that's driving everything that I've taught you so far. But we have to talk about Niels Bohr. We've got to talk about J.J. Thomson. We've got to talk about their results and Rutherford and some others and start tying this all together. And so I want to take you through the history of atomic theory. This is going to act as a break. Not only is this a bit of a break for us with all of this quantum mechanics we've been doing, but it's going to serve as a bridge to show us the way towards absolute quantum theory, our today's understanding of quantum theory. And the other reason we need the history is because, well, quite frankly, as they were making mistakes in early atomic theory, they actually developed the vocabulary that we use today. So context for where the vocabulary comes from becomes important in understanding what's going on. So we're going to back up right back to 1897. Well, we're going to start there. Now, granted, the history of quantum mechanics probably started earlier, but we'll stick with 1897 as a starting point because it's 1897 that electrons are discovered. Think about that. When I was in college in 1997, we celebrated the 100th anniversary of the discovery of the electron, right? We didn't know electrons were a thing previous to 1897.
I thought that's where they shot stuff at a golden plate.
That's coming up. This is before that, right? So in 1897, J.J. Thomson, pictured here, discovers actually what he discovers is something that he called a cathode ray. They had these things called cathode ray tubes. And really one of the reasons that the discovery came so late is because it wasn't until the 1880s that we had a good way of making a vacuum tube. That's why really light bulbs didn't happen, because what you needed was a glass tube, right, that would let light out, but that you could pull all the air out of it. Because if you try to light a filament in air, it combusts and burns and reacts with the air. So you need to get all the air out. And so, along with light bulbs, are these things called cathode ray tubes. Literally just two plates that you could connect wires to. If you sucked all the air out, and then put, say, argon or nitrogen or oxygen back in, you could see a beam. Light would happen, but there would be charges moving between the plates inside of this cathode ray tube. And
who's the guy that discovered how to do that?
I don't remember. I don't remember that. Okay, but it was, J.J. Thomson and others were trying to figure out what was going on, what made up these cathode rays. And what Thomson discovers is that they're negatively charged, and he has this kind of ratio that he couldn't, in his experimental setup and the theory, he couldn't separate the charge to mass ratio. He was measuring the whole ratio. He knew it was negative charge, but he didn't know the mass of the particles that were there. So he couldn't actually determine what the actual charge on a cathode ray was. Well, it turned out later to be the electron. And in 1906, Robert Millikan was toying with an apparatus called the oil drop experiment, where he took little tiny droplets of oil, little mist of oil, would negatively charge it, and then suspend it in an electric field rather. And by balancing the gravitational force acting on that little droplet of oil and balancing with an electric force pointing up, he was able to separate out the charge and the mass from each other. And so depending on how you want to sort of decide when we discovered the electron, really J.J. Thomson discovers the electron first, and then later, 1906, Robert Millikan would separate out that charge and that mass, and we would get really more understanding about these small negatively charged particles. And J.J. Thomson becomes the first to develop a modern atomic model. Now, previous to Thomson, we were playing with this idea that atoms exist, that molecules exist. The chemists, all the way back to the 1600s, and the law of definite proportions and things like that with Boyle and others, are discovering that if you react a certain amount of one substance, a certain amount of another, they always react at the same amounts, the same ratios. And they're conceptualizing this idea of molecules. Of course, the Greeks first came up with the concept of the atom, the atmos, this indivisible thing, right, the smallest unit of matter. But, I mean, really, it's 1898 when J.J. Thomson comes out with the first modern model for an atom. And I don't know, have you heard of this one before?
Yeah.
Plum pudding model. I've noticed that chemistry textbooks more and more, used to be chemistry refused to admit that this was even a thing. It was like an embarrassing thing in their past they didn't want to talk about, right? But it's important, okay? And it's important on a lot of levels, especially for science literacy, trying to understand what's going on here. J.J. Thomson was British, and plum pudding is a meal, dessert in Great Britain. It's bread pudding. So you take bread, usually leftover bread, it's kind of stale. You dump a whole bunch of milk and honey. Have you ever had a fruit cake?
Yeah.
It's a little bit like fruit cake. Not quite as dense, because I'm convinced that some fruit cakes are born in the hearts of dying stars when they go nova, right? It just compresses all the atomic matter together. But bread pudding is softer. If you've ever had rice pudding or flan, right? Well, dulce de leche is kind of like it pours, doesn't it? Oh yeah, that one. Okay. Rice with milk. Right? Okay. So it's kind of like that, but in Britain they'll take that bread pudding and they'll put dried fruit inside of it. And usually that fruit is raisins, which the British call plums for some reason. I don't know, look at it. Plum pudding. Anyway, it's got fruit in it, right? And so J.J. Thomson comes up with this model where he's thinking of the atom like a plum pudding. Namely, these electrons, these charges that he's found, okay, are like the raisins in plum pudding. The atom is this lump of positively charged stuff. And inside that positively charged stuff sit the electrons. Now, we have the benefit of modern science, and you've been through school, so you know what atoms, look, at least you think you know what atoms look like. I'm about to destroy that probably on Wednesday. But this is wrong, right? Like, patently, this is like, okay? But how do we know it's wrong? That's probably a more interesting question, right? Because knowing how we're wrong is essentially 99% of science and engineering. What can go wrong? Can we avoid it going wrong? And when it goes wrong, what can we learn from what went wrong? Okay? So I've just described your entire career if you're in any kind of STEM field. Right? Now, doctors try to do the not went wrong part. Right? You don't sit there over the body and go, gee, what went wrong? You try to prevent those things from happening in the first place. But they learn, right? But in STEM fields, we try to, we admit we were wrong and we learn from it. And there's not a bad thing to be wrong. It's just we got to be able to change how we see things. How did we know that Thomson was wrong? The answer is an incredible discovery. Okay? The discovery of radioactive materials. After our exam on relativity and quantum mechanics, which is coming up 2 weeks from tomorrow, okay, we will jump headlong into nuclear physics and talk about radioactivity. So I will tell you more about this discovery later on. Okay? But suffice it to say, 1 year before J.J. Thomson discovers the electron, Henri Becquerel discovers radioactivity. Again, I'll save that story for a little bit later because it's not totally pertinent to what we're talking about now. In this discovery, they're able to isolate alpha, beta, and gamma rays and particles. These are just 3 broad categories of radioactive particle. And it's this discovery of radioactive materials and the energies they're giving off that convinces a young Kiwi scientist named Ernest Rutherford, who was born in New Zealand but then came back to Great Britain. His family came back to Great Britain when he was a teenager. Convinces him that there's a way to use this newly discovered radioactive emission to probe the nature of matter and to find out if Thomson's model of the atom was correct. And so Ernest Rutherford conceives of an experiment where he takes a radioactive source of alpha particles. These are the heaviest of the radioactive particles. We now today know that an alpha particle is a helium nucleus. So you take helium, right, which consists of 2 protons, 2 neutrons, and a couple of electrons around the outside. Strip off the electrons. That's what an alpha particle is. Okay? They're born in processes that we'll talk about later when we get to nuclear physics and we start talking about the nucleus of the atom. But they are the ones that carry not the most punch. They don't have to be the most energetic, but they certainly want to interact with things the most of alpha, beta, and gamma. So he takes these alpha particles, takes an alpha source, points it at a leaf of gold foil. Now, I keep asking the district to buy me gold for science.
I wonder why they don't.
Right, and they keep refusing, right? Okay, then can I have diamonds? Like, you can do stuff with that, and like, no, can't have diamonds either. But if you've ever seen tinfoil, you know what tinfoil is, right? Okay, how many of you have seen gold leaf foil, like it's used someday? Yeah, so some of you have. You can tell me, right, and just acknowledge it's really thin, isn't it?
Super thin.
Like super thin. It's always trying to stick to things, right? Okay, so gold can be made really, really thin. So this is what Rutherford is using. He's using just this thin gold foil. And he's shooting alpha particles at it, right, to see what happens. Now, if atoms were made of goo, positively charged goo, and an alpha particle is positively charged, right? It's got 2 protons, 2 neutrons, and no electrons. If you've got that set up, then what do you expect to happen when you shoot the alpha particles at the foil?
It'll bounce off.
It should bounce off, right? But that's not what Rutherford sees. Instead, what he sees is a majority of the alpha particles going through the foil, as if it weren't even there. Every once in a while, an alpha particle would get deflected in the forward direction. In other words, it passed through the foil, but it had been pushed out of its trajectory. And so he has this screen. This picture is the final experiment, but the original experiment, he just had the screen on the opposite side of the foil, right? Because he was fully expecting there to be no alpha particles. So he put a screen back there, right? And in the case that maybe 1 or 2 made it through because there were holes in the foil, he'd know. But no, what he's seeing is most of the alpha particles come through, right? So he gets really excited and tries to understand what's going on with the atom. And the conclusion he's drawing, right? The fact that the alpha particles are passing through the foil and some of them are kind of getting deflected, what conclusion do you have to draw? It's mostly empty space, right? These alpha particles are just blasting through the foil. Foil seems to be unaffected, right? But they're going through. And every once in a while, one of them's deflected. So what's happening in the foil? It's hitting something, right? Okay. Something is deflecting these particles. And so he starts doing conservation and momentum calculations for the alpha particles and things like that. He's coming up with some really, really interesting things. Like, the atom, the mass of an atom is concentrated in a really tiny central point, right? But then the rest of the atom is mostly empty space. There's room between the gold atoms for these alpha particles to pass through. We'll get back to Rutherford in a second. But we need to tell you about a couple of Rutherford's graduate students. See, this experiment required a detector screen that was not electronic, right? We're back in the age of we barely made light bulbs, right? And so they don't have any detector apparatus, nothing like that to do it automatically. And so to pull off this experiment, you have to set up the apparatus in a room with no windows and completely blockade all the cracks in the door. Okay? And then turn off the lights and wait for 30 to 40 minutes in pitch black darkness for your eyes to get sensitive enough, right, with not having any light hit your eyes, to be able to see the little tiny flashes that were being given off as the alpha particles struck the detector screen.
Oh.
Yeah, right, in our modern age where nobody can go more than 2 seconds without staring, right, at their device, okay? What do you do with 30 or 40 minutes of pitch blackness? You can't see your hands in front of your face. You think, don't you? So Rutherford's thoughts went along this line. I don't want to be here. I don't want to be here. I don't want to be here, right? So he assigned his graduate students to do the experiments. Right? Because what are graduate students? Indentured servants is what yes, okay, but they'll do anything, right, for a grade. You had a comment?
I was curious what the detecting screen was made out of.
It was made of a material that fluoresced when the kinetic energy of the alpha particle strikes it. I don't know exactly what that material is. Okay? It was really, really tiny flashes, right? So that's why they had to wait till their eyes were sensitive enough to be able to see them, right? Okay, and even then, it was more like sort of a statistical population study than it was an actual counting of individual hits, right? So Rutherford's graduate students sit down, right, and again, they're running the experiment, and while they're waiting for their eyes to adjust, you can imagine that they're sitting there talking, right? Okay? And what do you think they're talking about while they're waiting for their eyes to adjust? I don't want to be here, I don't want to be here, I don't want to be here, but we're stuck. So I wonder, is there a way for us to design a system that can count for us? One of the graduate students' name was Hans Geiger. Geiger would go on to develop an instrument, a tool, called the Geiger counter. That was designed to do what?
Yeah, the radiation.
Count radioactive particles. Necessity is the mother of invention, isn't it? Okay, right? But before that would happen, Geiger and his fellow graduate student, I can't remember his name. It's not going to come to me, I have to go look it up. Who didn't do anything famous to get anything named after him. They were noticing, right, as they were running these experiments, that there were some pretty extreme angles that were being produced. And so they asked Rutherford for permission. They said, can we extend the detector screen and do almost a 360 all the way around the gold foil? And Rutherford kind of ridiculed them a little bit. He's like, well, why do you want to do that? Right? There's not going to be anything back there. Right? And they're like, well, we've got some extreme angles, and we just want to double check and make sure that there's nothing fishy going on. So Rutherford's like, okay, fine. So they did that. And lo and behold, they got detections, a lot of them, okay, from what we would call maybe the backside of the foil on this diagram. Okay? So most of them, again, were coming through. Some were being scattered at large angles, but more were bouncing off and getting scattered backwards, back towards the source, right? At extreme angles. What does this mean? They're bouncing off, right? They're hitting some. These alpha particles, which are like a freight train, okay? Coming into this gold foil, right? Which is like a car on the tracks, okay? Is bouncing off and coming straight backwards. This is craziness. And when Geiger and his fellow graduates ran to tell Rutherford, he didn't believe them. He said, well, you're setting it up wrong. You've got stray particles coming out of the source that are hitting this. It's like, no, we set it up right. So they grab the boss, right? They bring him down, right? And you can imagine that 40-minute discussion. You guys don't get degrees if this is wrong, right? I don't know what was going on in there, right? But then they turned on the source, they lifted off the cover, and lo and behold, Rutherford saw with his own eyes that his graduate students weren't wrong. That they were seeing these hits on the backside of the foil. When Rutherford later would talk to the public about that experience, he would use an analogy to try to describe how astounded he was at what he was seeing. And this is, he's discovering this in 1906, 1907. He is delivering a talk in 1915, I think. And this is the run-up to World War I. And so it was very much in the public consciousness, this concept and idea of the battleship. And on a battleship, you have these huge guns. And the guns on a battleship are used to bombard shore targets and shoot other ships and things like that. And on these ships, they would rate the power of the gun by the diameter of the barrel. Right? So on the battleships of the time, they had these things called 16-inch guns. Which means that the bullet that they're loading into the gun has a 16-inch diameter. Okay? That's the projectile, right? The gun itself, right, was tens of feet long, right, on these battleships. And so Rutherford described to the public, he said, it was as if, experiencing this experiment, was as if you were sitting in a chair and I pointed a 16-inch gun at your face and then gave you a tissue to protect and defend yourself. The 16-inch projectile is the alpha particle. The tissue is the gold foil. And imagine to your surprise when I fire the gun and the shell bounces off the tissue. What's that? Cannon that was 76 millimeters? About like that? And you thought that was big? Right? Okay. How heavy were those projectiles? Yeah, okay. He said it, not me. Right, okay? But yeah, they're heavy. Okay? These guns required like loaders. They required these hydraulic systems to load because they couldn't lift the. Anyways, so that's kind of the level of astounded. Like you can just imagine Rutherford and his graduate students going, "This is not possible, right? This is not possible."
What was expected? Like if the whole plum pudding thing was just bounce off. Right?
It should have just bounced off, right? Okay, but obviously most of them are going through, right? But then you get ones that come directly back. Like scattering angles of like 160 degrees. That went in and came right back out again. Okay? That shouldn't be happening. It should be blasting right through, right? So Rutherford decides that J.J. Thomson's model is incorrect, right? He's got experimental evidence to suggest that it's not plum pudding. It's in fact mostly empty space. And so he coins a term, the nucleus, right, for the concentrated center of an atom. An atom is mostly empty space. Almost all of its mass is contained down at the center, okay, and is positively charged. The term proton is coined to describe the positive particles that are all lumped together in that nucleus. Later, Rutherford would realize that there's too much mass in the nucleus, according to his calculations. Not enough protons to compensate for that mass, so there must be another particle down there that has no charge and just mass. What are we going to call that one? The neutron. Okay. So we're getting the evolution of all the terms, right, that we use today to describe the atom. And then he's looking for a way to try to handle these electrons, right? these negatively charged particles, right, that aren't inside the nucleus, right? Again, he says the atom is mostly empty space, but it has to have a structure. And so he's looking for anything in nature that he can draw an analog to, and he needs something that where 99% of the mass of the system is in the center, and 1% of the mass is doing something elsewhere. What does he reach for? The solar system, right? Because that's a description of our solar system. 99.2% of the mass of our solar system is the sun. Okay? The other 0.8% are all the other planets and asteroids and aliens and whatever that are out there, right? Put together. Okay? So we are the 1%. Actually, we're much less than the 1%. So he adopts this so-called planetary model of the atom. Okay? Again, dense nucleus consisting of protons initially, but now protons and neutrons. Electrons are in orbit around that nucleus. That's what gives the atom its volume, right? The outermost electron, furthest one in orbit, right? Kind of like the planet Uranus, right? Way out there. And then you've got more electrons that are closer in, like the inner planets, like Mars and Mercury and whatnot. And so here's something that can be mostly empty space, and yet still have structure, right? It's consistent with the experimental observations that he's doing. So he goes and he calculates, right? Okay. He coins a definition, a phrase, called atomic number. Atomic number tells us the number of protons in the atom, the number of protons in the nucleus of the atom, to be specific. He goes and calculates the radius, and he gets a radius for his atom of, just a little like 10 billionths of a meter, okay, which is really, really tiny, okay. So there's an analogy on the screen there, okay. So if you look at your pen right now, okay. Your pen or your pencil has got a little tiny tip on the end, okay? If you look at that little tiny ball bearing, if you were using an ink pen, or you're looking at the little tiny piece of lead that's sticking out, if you have a 0.5 or 0.7 millimeter lead pencil. If you take that to be the size of the nucleus, and you're standing in a football stadium, American football, okay, on the 50-yard line, then the closest electrons, according to Rutherford, are in the end zone. And what's between the closest electron and you?
Space.
Nothing. Actually, it's not nothing. I'm of the very firm opinion that the stuff that exists between the nucleus of an atom and the electrons is called olive oil. It holds the universe together. Okay, so I should not teach false science in this day and age. My family cooks with olive oil. My mother's maiden name is Carangelo. Belo is a Hungarian name. Comes out of the Mediterranean. We don't eat food unless it has olive oil on it. Right? So, anyway, right? This is a crazy, crazy structure. Let's do something maybe that's a little bit more closer to home. If I had a basketball right here, right, and I said that was the size of the nucleus of an atom, okay? You want to take a guess as to how far away the closest electrons would be?
8 miles.
Like, name a town. Not the moon.
Close.
Madeira.
London?
No further than Clovis.
Fraser?
Closer than Bakersfield.
Celia?
Yeah, it's about Selma.
Selma? Oh, that's a town.
45.
It's the closest one I got. Kerman is a little bit further away than Selma, but it's on the same order of magnitude of 1% error right there. Okay, but Selma's the one that I calculated was the closest radius to Fresno City College. And again, everything in between, from Selma to us, right, is empty space. There's nothing there. Okay?
How does the universe hold itself together?
Well, yeah, it's right. Okay, so Rutherford publishes his model, right, It's 1907. He's publishing his preliminary findings, 1908. Rutherford would go on to win the Nobel Prize for this discovery. Now, Rutherford was famous for being kind of a jerk. He was full of himself. And he was a physicist. He believed physics is the chief science from which all other sciences are derived, right? Okay, and nobody can get anything done unless the physicists are around. And he seemed to have a particular dislike for chemistry. Matter of fact, he referred repeatedly to the science of chemistry as being nothing more than stamp collecting. Okay? In his mind, chemists weren't doing anything novel or new. They were simply categorizing all the different elements, categorizing all the molecules, figuring out all the permutations of reactions. And he said that's stamp collecting, right? He's being very offensive, right, to the chemists. So, what does he win the Nobel Prize for? Chemistry. And he was so mad.
Wait, not for physics?
He did not win in physics, ever. Okay? He would win in chemistry. He would try really, really hard to win in physics.
He was a premier stamp collector.
Yeah, so he was a premier stamp collector, yes. And I'm sure something that he
Is
regretted.
there a reason why in chemistry you just like
Because back then, this was considered chemistry. You're probing the nature of materials,
chemistry?
right? Okay. Does anybody know who the first person was to win 2 Nobel Prizes in their lifetime, one for physics and one for chemistry?
I definitely remember.
Was it a woman?
Yeah, it was a woman.
Which woman?
The one that discovered radium.
Marie Curie.
Radium.
Yeah. But we'll get to her in a little bit. She was also the first person to win 2 Nobel Prizes.
I want to know like what kind of calculations they do where they can bounce off of it, but they can derive all this information. Just
Conservation momentum, classical physics, conservation momentum problems. You know the mass of your alpha particle. You know roughly the mass of a gold
I thought
nucleus.
that like broke down once things got really, really small.
But they didn't know that yet. Right? It's 1907, 1908. Right? Einstein has published his papers, but Rutherford probably doesn't understand them. Nobody does. Right? These are papers that are like, wow, these came from nowhere. We don't care. Right? You don't have any experiments to back it up, so, right? Einstein wouldn't be till 1919, right, that Einstein would just become the major force that he was, right? So yeah, they don't know any different, right? Okay? But I'm glad you brought that up because we're going to start seeing a breakdown in science now, okay? In physics particularly, right? If we go back to Newton and we talk about things that are moving in a circle, what kind of motion is circular motion? It's accelerated motion, isn't it? Anything moving in a circle is experiencing an acceleration. In this case, a centripetal acceleration. Not because its speed is changing, but because the direction is changing, right? Which means that there needs to be a force on that particle, right? Well, it's easy to imagine what the force is between a proton and an electron. Physics 4B students, what's that called? Coulomb's law, right? The very first force law that we learn in Physics 4B after we get out of the terrible thing that is thermodynamics is Coulomb's law, which is, everybody knows this one. You don't have to take 4B to know that what happens when the positive and negative thing get together? They come together, right? So we can see that there's a force of attraction, like gravity, right? Pulling the electrons and protons together. But the electrons are in orbit, so they're moving in circles, which is accelerated motion. Which means the electrons are accelerating, right?
So that always.
Right? You with me?
Yeah.
This is basic physics.
If they're changing direction,
If they're changing direction, they're accelerating.
Yeah.
That's right.
But Maxwell has shown us what happens when you accelerate any charge. Not just current,
Electric.
but electromagnetic waves. So what should these electrons be doing?
Getting off light.
Giving off electromagnetic radiation. That's an energy loss. And if you decrease your orbital energy, what is happening to the distance between the proton and the electron?
It's getting closer.
Getting
together.
smaller. If you go and calculate how long that takes, it's on the order of a nanosecond for the electron in a hydrogen atom to spiral down and collide with its nucleus and then be annihilated or absorbed.
You can shrink pretty fast.
Everybody look at your thumb. Is it still there?
No.
It's still there. Yes.
Kind of a wave, right?
The answer is a wave.
Not looking.
I just turned my thumb into a wave, right? Right? Okay. So it's unobserved back here, right? Okay. So obviously, atoms aren't doing this. Atoms are stable, right? The electrons are doing something in these orbits so that they're not decaying in their orbits, right? However, this is a huge, huge problem. This is like we're breaking physics problem. Okay? And when Rutherford publishes, he acknowledges, right, that he does not understand what is going on. This is the results of my experiment. These are the conclusions I'm drawing. We need to figure this out, right? That's one of the reasons you publish, is to say, look, I've discovered something, I don't get it. Here's my best guess. Help. Like, and this is what science is about, right? You see somebody else, you try to replicate it, and you also try to explain, maybe tweak it a little bit, right? And move forward incrementally, step by step, throwing out the garbage, winnowing down to the truth. So Rutherford is not so egotistical that he's not like, oh, I'm right, you're all wrong. He's a jerk, but he also is saying, look, there's something very wrong here, right? These electrons should be annihilating themselves on the nuclei. They're not. So more study is needed. Okay? But it's an important model because it gets us closer to what we know today is the correct one. Right? We've moved from plum pudding to a model that is mostly empty space. But the puzzle continues to come together. Because while electrons are being discovered, while radioactivity is being discovered, and while Rutherford is poking around with his atoms, we have black bodies. Remember black bodies? Max Planck, 1903. Albert Einstein, 1905, describes the photoelectric effect, giving us a concept, an idea of what E equals HF really means. Do you see how everything's all starting to come together here? The turn of the 20th century must have been a really exciting time, right? In physics, when so many things are happening simultaneously that are all going to come together here, right? To help us understand what's going on. So, we've got the black bodies going on, okay? And then we also have these things called the spectrum of gases, okay? Also called spectral series, okay? And they look like this. We actually have talked about this before. When we talked about diffraction gratings, I gave you the groovy glasses, right? And then I held up different gases, electrified gases, and we were able to see that the diffraction gratings in those glasses were able to produce the line spectra, the fingerprint of those elements. So here's some. We got hydrogen on the top, mercury there in the middle, neon on the bottom. You can have emission spectra where you charge up a gas or you burn a material in a flame and it gives off the light, and then you use a diffraction grating to separate it out. You can also have an absorption spectrum where you take the gas in a glass tube, hold it up to like sunlight, which contains all of the colors of the rainbow, and then you see places where there's absorption going on, there's missing wavelengths and frequencies in that absorption spectra. But the absorption spectra for hydrogen and the emission spectra for hydrogen line up. Okay? So this is something that had been discovered in the 1870s, 1880s. There was an English high school teacher by the name of Balmer, last name
English?
of Balmer. He was English. No? Somebody want to correct me? Wikipedia. Pretty sure he was English. Last name of Balmer. And what Balmer had done is he was looking at the hydrogen spectrum. Okay? And in his spare time, he developed a mathematical fit to the relationship for the four colored lines you see in this diagram. The other black ones he actually couldn't see because they're outside the visible spectrum. They're out there, but he couldn't see them. So what he does is he comes up with a mathematical model. And this is what his model looked like. Again, he's not deriving anything. He's taking a look at the distribution of frequencies and seeing if he can't find a function that fits that distribution. So this is the function that he comes up with. It's kind of a modern take on it. But he found that the inverse of the wavelength associated with that color. So again, here's wave-particle duality rearing its ugly head, right? We have a frequency, which is a particle-like thing, that is color. But we can talk about that color in terms of its frequency or its wavelength. Balmer's choosing to do it in terms of wavelength. But he finds that the inverse of the wavelength that you get in the hydrogen series is equal to a constant, R sub h, times the quantity 1 over 2 squared. I'm writing it. I don't want to write 4 for a reason that I think you probably already know, right? But we'll get to it in a second. Okay, minus 1 over n squared, where n is equal to 3, 4, 5, really any integer. But when you put n equals 3 in there, you get the red one. When you put n equals 4 in, you get 486. You put n equals 5, you get 434. You put n equals 6, you get 410. Okay? So this function right here, which is known as the Balmer series, right? Again, is a mathematical result. He knows what the frequencies are. He wants to find the mathematical relationship. And lo and behold, it's not something ugly. It's not something transcendental. It's not, right? Okay? It's actually following a pattern based on integers. The constant sitting in front is called the Rydberg constant. It has a value of 1.097373 ... times 10 to the 7 inverse meters. Now, most of the time I do not write constants with that many significant digits, right? But I wanted to underscore something. How well do we know the Rydberg constant?
Very well.
Pretty well, right? So that's why I wrote all those down.
So positive 7.
Positive 7.
Eat the positive 7.
Okay. And so you have these line spectra of the gases. And Balmer did it for hydrogen for the visible. There would be others that did other line spectra for the ultraviolet and infrared and some other things. They would have different names, okay? And they discovered later on that I wrote it as 1 over 2 squared. But if you do 1 over 1 squared, you start getting the ultraviolet lines, okay, the ones that are beyond the purple. Okay? If you do 1 over 3 squared as the first thing in there, then you get the infrared ones, okay, the ones that are beyond red. So there's these different ones, and each series has its own name. Like, and the ultraviolet are the Lyman series, and the infrared is the Brackett series, no, Passion series. And anyway, the different names for the different people that found them, and then were able to follow Balmer's lead and fit the mathematical equation to it. So, what does this have to do with anything? Remember, Rutherford publishes 1907, 1908 on the heels of J.J. Thomson's work. Simultaneous to this, we have photoelectric effect, the Planck-Einstein relationship for the energy of a photon. Relativity is going on, but that doesn't impact us here. We've got this line series that was discovered in the 1880s, and nobody had a good explanation for why it was like this. They just had the math for it. This all culminates when the button gets pushed. There we go. Okay? All these pieces of the puzzle come together and fall in the lap of Niels Bohr. Niels Bohr was Danish, hence my pun. Okay? And in 1912, he visits Rutherford in his lab. Okay? And I don't know if there's any other way to describe it. That visit changed Bohr's life. Like, Bohr was at this point he was a professor of physics, I think. But he had just recently graduated. And he's trying to establish himself at the University of Copenhagen. And, he's looking for research to get into. And basically, he visits Rutherford. He sees what Rutherford's doing. He sees the atomic model. And it's like, our universe changed on that day. Because Niels Bohr, in that moment of childlike glee and wonder, he was just that kind of person, right? Would say, I'm going to study this. And it only took a year. Right? For him to start putting the pieces together. Niels Bohr was a tremendous, tremendous character. As alluded to in one of your videos, he enjoyed ping pong quite a bit. He would argue with his professors and later his graduate students over the ping pong table. He had some kind of learning disorder. He was unable really to write anything down that he could comprehend, let alone anybody else. It was probably a form of very extreme dyslexia or related motor difficulty.
Wait, you can't write?
Yeah, he just couldn't write things that made sense, even to himself. And so to get through school, he would go to his lectures, he would listen, he wouldn't write anything down, and then he would go home and he would dictate to his mother everything that was in that lecture. The math, everything, right? Describing to her, because she didn't know the math, describing to her what an integral symbol looks like, right? And all these different things, right? And she would write it down for him. Okay? And this is how he went through school, right? He developed this incredible ability to sit and listen and memorize and then go home and give that out in words for his mom to write down. He was a handsome young man, and as handsome young men and young women tend to do, they fall in love, and so he was engaged, and as his intended got to know him better, right? She started taking over the role of recording things down for him. She was educated in her own right. She wasn't a physicist, but she had enough of a grasp of mathematics and things like that to be able to follow along, even to a point later on in their marriage when she was able to correct his mistakes in the math. Because he would dictate derivations to her. He would just be speaking his derivations. Because he couldn't really write it down to save his life, right? Okay? Every time he tried, it would just kind of come out as gobbledygook. And so he would be dictating things, and she would catch errors like, oh, you didn't carry the 2, or you missed a minus sign, or did you really mean that symbol? I think this is the symbol you meant. So they were a great team working together. We are indebted to Mrs. Bohr, both of them, mom and wife, right, for what we know about recording his science and being able to publish and being a part of the scientific community. So we can't count them out by any stretch of the imagination. One last story about Mrs. Bohr, because she's such a phenomenal woman. They're married, right? And back then you get married, and then they were waiting for sort of the end of the semester to finish so they could go on their honeymoon. And they had scheduled a month-long honeymoon through continental Europe on the train and all that sort of stuff. 2 days before they were to leave on their honeymoon, Bohr comes running into the house screaming that I've got it, I figured it out, and I need to get it down on paper. So she assumes, right, she goes to the desk and she's ready, right, okay? And he says, this is going to take more than 2 days. What he had figured out was what I'm about to tell you. What we would later, no, it's not going to take more than 2 days. But, because we're going to skip a lot. But he had figured out the atom. The Bohr model of the atom that you've studied probably in chemistry, in high school or anywhere else, okay? He's got this in his head, right? And he tells her it's going to take more than 2 days to get down. We need to postpone our honeymoon. She looked at him and she said, yes. They wrote for 2.5 days. They wrote and slept and wrote and slept. And it was finally down. They missed they got their honeymoon later, for those of you who were worried. They didn't. They finally went on their honeymoon, right? But because of her, we have the Bohr model of the atom. Right? And the first quantum model of the atom. Hooray, Mrs. Bohr. All right. So, what's so amazing about this model, right? What is it that Bohr has cracked, okay? So, the problem with Rutherford's model are these electrons that are in these orbits, right? And the orbits should decay. So Bohr is trying to come up with some sort of concept and idea, both figuratively and mathematically, that would explain why the electrons aren't giving off energy, right? What's going on. And so he hits upon this idea, and he's able to later derive it in the mathematics, where there aren't an infinite number of energy states, orbital states, that can exist. Okay? In our solar system, the planets are where they are in our solar system for many different reasons, but they don't have to be where they are in their orbits. In other words, Earth could be closer or further away. It's just that because of the distribution of mass in our early solar system and how those masses coalesce, we are in the position where we are now. But it isn't to say that, like, the orbit between Earth and Mars, you can't have a planet. You can. There's nothing that's classically preventing that from happening. But in Bohr's model of the atom, what he's saying is, no, these electrons can only have certain orbits. There are allowed orbits, and then the rest of them are not allowed. In other words, the orbital energies are quantized. Right? He has discovered, or he's linked in the idea of Planck's E equals hf, the fact that the energy coming in light is in packets or chunks, and he's applied that to Rutherford's model and tried to figure out how that would be.
Are the orbits like dependent on the neutron?
Nope.
Or, yeah, nucleus.
Turns out that they are dependent on the angular momentum. This is Bohr's big discovery. He discovers that the angular momentum of electrons in the hydrogen atom is quantized. Not an infinite number of allowed angular momenta, but in fact, angular momentum that are very much singular in their states. You can have multiple states, but between states, you're not allowed to have anything that's in between. So, yeah.
Have we explained why?
Not yet.
The warp is overrated?
Okay? And as this slide is telling you, it's kind of, spoiler alert, the Bohr model is not able to explain why these electrons are not radiating energy. So Bohr's hit upon this quantization of angular momentum, but he cannot explain why these electrons going around the nucleus aren't giving up energy. We know the answer. Why don't they give up energy? There's only one answer to gain. That can be right. They're not giving up energy because they're not going around.
Oh.
We're going to get there. We're going to get there. Okay? Because this isn't the end of the story. We have the entirety of quantum mechanics and Erwin Schrödinger to apply to this,
Are
right?
they jumping?
Okay. Bohr then starts looking at the energy levels and realizes that the electrons can transition from energy level to energy level. So he calculates what these energy levels are. He then looks at the differences in the energy levels and the jumps that are happening. And he looks at the Balmer series. He looks at his calculations for the atom. And he looks at the Balmer series. And guess what he finds?
They match.
He's in exact agreement for the Balmer series. Bohr has discovered exactly why hydrogen gives off that characteristic set of lines. What are the electrons doing?
Jumping.
Jumping from energy level to energy level. And as they do that, they have to give off energy in the form of a photon. That photon is quantized. It always comes out as one of those 4 visible wavelengths. Those 4 visible wavelengths correspond to all electron transitions that happen down to the second energy level. In the Balmer series, it was 1/2 squared. The reason we write it like that is because the electrons end at the second level, but start at the 3, 4, and 5th energy levels. Bohr would then be able to show, look, there's other transitions. Go look for them, and everybody else would go look for them, and lo and behold, they were there exactly matching. So Bohr's model of the atom explains the Balmer series and all the other series. It gives us a reason for why there are very specific orbits that are allowed in the atom, so it's an extension of Rutherford's model, but it does fall short on being able to explain 2 things. Why those orbits are special, and number 2, how does the electron jump from one orbital energy to the other? To get from Mars to Earth's orbit, what do you have to do? You got to go through all the orbits in between. It's called a Holman transfer orbit. It's got a specific mathematical curve. Bohr's like, that's not happening here. The electron is in one energy, and then it's in the other, and it did not move in the space between. Because the space between is not allowed.
So it's just sitting there. If you put energy to it, it just sits there, gathers it, and then at some breaking point, just pops into another orbit.
Yep. It gains or loses energy in the absorption spectrum, right? Photons are absorbed at those wavelengths because those photons have the energy that exactly matches the jump moving the electron up. In the emission spectra, it's the electron coming down, giving off that photon.
So is it kind of like they're teleporting?
No.
They are already there.
So, Bohr's model makes the assumption, okay, that it's only electric force law that's involved here. So Coulomb's law is the thing that's active, okay? There's only certain orbits that are allowed. The electron transitions are dictated by the Planck-Einstein relationship. You have to have exactly the right energy, which is why it corresponds to these frequencies. And that the allowed orbits are determined by the following quantized angular momentum. The angular momentum of an electron in orbit around the nucleus of a helium atom is n, an integer counting number, times Planck's constant divided by 2 pi. And we've seen Planck's constant divided by 2 pi before, haven't we? It's h bar. And we know h bar shows up in all the nasty quantum mechanics. This is where this is headed, right? So, n is an integer. 1, 2, 3, blah, 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 blah. Okay? We have an electron, right, that's orbiting around with some tangential speed v. It's got the mass of the electron. It's got a distance from the center. And it's the electric force, right, that's pulling it towards the center. So, we have, okay, and Bohr puts together, first of all, Newton's second law. Okay, classical physics, right? And Coulomb's law. Again, I'm sorry 4A students. You can go ahead and think of this one just like gravity. Okay, but instead of mass being the things that are being pulled together, it's charge. Okay, different charged objects, and you know the basic rules, right? But there, K is an electric force constant, don't worry about the number. And then Q1 and Q2 are the charges, so you're multiplying the amount of charge together, divide by distance squared, behaves just like gravity, half the distance is quadruple the force. That's called Coulomb's law. And then because it's moving in a circle, we know the centripetal acceleration is going to be v squared over r. So if you take these three equations and you put them together, you can derive the radius of all the orbits in Bohr's atom. It's going to be n squared h bar squared over mass of the electron, electric force constant, times charge on the electron squared. The symbol E is charge on the electron. 1.6 times 10 to the minus 19 joules. And if we go ahead and we say, you know what? We've got a constant factor that is floating around out here, right? Okay, it's h bar mass. Okay, that's not changing, right? Really, all it's doing is changing n. Everything else is a constant. Then we can write the radius of any single one of these orbits as n squared times a naught, which is why a naught is often called the Bohr radius. Okay, you put n equals 1 in, right? You get the ground state. So a naught's referred to. It's a number. Okay, that comes about. The thing in the box you have derived. Lab number 1. Problem number 3, 2, one of them. Okay, I gave you the 4 green boxes and said come up with the red box. I didn't tell you why. What were you doing?
Substituting.
Quantum mechanics. Classical quantum mechanics. You were doing the Bohr model. You derived that thing. Go back and look at lab 1 if you want to see how all that's done. What I want to do is I want to take this in a slightly different direction. Okay? And again, do what Bohr did, which is, let's take a look at it from the point of view of energy considerations. Let's look at the energy of one of these electrons as it orbits. Okay? We know that that energy is going to be a combination of the kinetic energy and the potential energy. And so that's going to be 1/2 mv squared for the kinetic energy of the electron. And then here's what gets a little bit dicey. What direction is the force pointed on the electron?
Inward.
It's inward, isn't it? So 4A students, when we wrote down gravitational potential energy, it ended up as being G m1 m2 over r with a negative sign in the front of it. And in order to not be connected to the Earth, gravitationally speaking, you had to have a positive potential energy. Anytime you were being gravitationally influenced by the Earth, you had a negative potential energy. Exact same thing is going on here, but it's not gravity. It's electrical force. So I'm going to write the potential energy as a negative. It's going to be plus a negative thing. And electric potential energy is electric constant times charge, both charges, products of the charges, divided by R. So I know that this might seem like a little bit of hocus pocus, but I've written down kinetic energy, we all know and love, 1/2 mv squared, and then the potential energy of an electron near a proton is given by that. 4B students will recognize it as electric potential energy, okay? But 4A students might be going, oh, it's a little bit weird. Don't get hung up on the details, right? We're going to investigate the end. What?
What does the comma tell you?
The comma? Q1. Q1 and Q2. There's got to be two charges in there. It's R. Thank you. You guys know me. I always screw this up. But I'm sure this time. The force is R squared. But the potential energy is R. 4A students, remember I used to make that mistake too? We were doing gravitational force versus gravitational energy, and I warned you. It looks almost exactly the same. It's just 1 over R instead of 1 over R squared. As units of joules, looks really close. Yeah, it can mess your brain up. Okay, but I didn't get that right. It's even in my notes, which maybe both are wrong, and that's okay. All right. So that's the energy statement. Let's just take a real quick look at Newton's second law. Okay, we know the force is electric force constant times Q1, Q2 over R squared. And since the thing is going around in a circle, we know that this is V squared over R. Okay, and you might be going, well, why do you want to all of a sudden do Newton's second law with this? I want a different way of writing V. I want to kind of get all of this energy. I want those two terms to talk to each other. And so I want a different way of writing V. And I've got it right here. If I get rid of one of those R's and my charge becomes the charge on the electron. Because what's the charge on a proton? Positive. What's the charge on the electron? Negative. What's the magnitude? Exactly the same thing, right? They're both the same magnitude of charge, the fundamental charge. Just one has a positive sign, one has a negative sign. I'm not worrying about the signs. I just want the magnitudes of the charges. Then I'll end up with Ke squared over Rm is my velocity. And that velocity can now be shoved in right there. This is 1/2 m Ke squared over Rm minus Ke squared over R. What happens to the m's? Cancels. What happens to, well, now I have a 1/2 Ke squared over R minus a Ke squared over R. What's that? What's a half minus 1? Negative half, isn't it? There's the energy. The energy that one of these electrons has. Okay? So, if then we follow this up with the fact that the distance is given by the Bohr radius, right? And we go ahead and throw this in there, then we will get an energy that is a function of n, a quantized value, that is equal to negative Ke squared all over 2 Bohr radius, and then just pulling out the 1 over n squared to emphasize the fact that it goes sort of inversely as n squared. If you then calculate the constant on the front, and you convert that constant, which is an energy, into electron volts, you get negative 13.606 electron volts all over n squared. And there it is. The energy values for all of the allowed orbits in the Bohr model of the atom. How many of you have seen the negative 13.6 before? Yeah? In chemistry? Did they ever talk about it in terms of electron volts? They do it in joules? Doesn't matter. The point is Bohr has derived exactly the relationships that he needs, right, to come up with this. The ground state, when you put if you put negative 13.6 divided by 1 squared, what do you get? And then you put in negative 13.6 divided by 2 squared, you get negative 3.4, so on and so forth. How far can you go? Infinitely far, but as you can see, they start running into each other up there. And as n gets infinitely big, your energy is going to approach what? 0. So if the electron has an orbit, an energy that is positive with respect to the nucleus, that electron is no longer bound in that atom. It's got positive energy. But if it's got negative energy with respect to the nucleus, then it's somehow sitting in one of these allowed orbitals. Let's go just one step further. Okay? We know that E is equal to HF via Planck-Einstein relationship, and that the frequency being given off by the hydrogen atom is going to be the energy difference when an electron transitions from one level down to the next, right? Then the energy of that transition is going to be the difference of the energies. Divide by Planck's constant gives you the frequency that's being given off. But that means, based on our result right down here, where our energy is Ke squared over 2A naught, 1 over n squared, that means when we take that difference and divide by h, what we're going to get is Ke squared over 2A naught h, 1 over n final minus 1 over n initial squared. I took the energy from the Bohr thing. And then, if we take the fact that the speed of light, the wavelength, and the frequency are all related to each other, and 1 over the wavelength is going to be the frequency divided by the speed of light, then 1 over the wavelength, according to Bohr, is going to be Ke squared over 2A naught, speed of light, times Planck's constant. What do you think the value of everything is that's sitting right there in front?
1.
Not 1. Not 2. No. It's the Rydberg constant. Because what is this? This is Balmer's series. And Bohr derived what the Rydberg constant is based on the fundamental properties of the system. Charge, Planck's constant, mass, so on and so forth. Right? So Bohr explains a ton in his model of the atom, and we're not done with him.
Oh my goodness.
Okay? We will continue to talk about him on Wednesday. Tomorrow in lab, we're going to talk about the nature of experimentation. Okay? Got a video, and then I got a little bit of lecture. We're going to talk about interferometers again. So we'll get there.
Oh man.
Those are ends in the final. My handwriting's bad.